In this video, we are going to explain how to use a slide wire potentiometer to measure small EMFs. Let us start off with this problem. Suppose we are given a potentiometer with a driver cell of 1 volt and the length of the slide wire is 1 meter. If we want to measure a potential difference of 1 millivolt, what is the balance length of the wire? From the principles of the potentiometer, we know that when no current passes through the galvanometer and the whole length of the wire is at 1 volt, hence 1 volt is proportional to 1 meter. If we are measuring a potential difference of 1 millivolt, then we can write that 1 millivolt is proportional to L. Putting these two equations together, we have L over 1 meter is equals to 0.001 volt over 1 volt. And L simplifies to 1 millimeter. Can you see the implication of this calculation? If the voltages that we wish to measure is significantly smaller than the potential difference across the wire, like in this case, if the voltages that we wish to measure is only if of an order of a few millivolts, we will be only using a very small part of the wire, and the readings we get will all be clumped up together, and the sensitivity of our voltmeter is not very good. So how do we solve the problem? Can we stretch the scale of the wire such that the potential difference of the whole wire is 10 millivolts? That will definitely increase the sensitivity of our voltmeter. Let me give you a clue here. Let us now look back at our potential divider circuit. Suppose I have a 1 volt cell that is connected in series with a 99 ohms resistor and a variable resistor of maximum 1 ohms. What is the minimum value you can get for the potential difference across R2? What is the maximum value you can get for the potential difference across R2? Let us quickly work this out. In both cases, we can use the potential divider principle to find our answer. The minimum value of V2 occurs when R2 is 0. Hence, V2 is also 0. Maximum value of V2 occurs at maximum value of R2, that is 1 ohms. Hence, V2 is equals to R2 over R1 plus R2 times VB. And that gives us 1 over 1 plus 99 times 1. And that works out to be 0.01 volts, which is 10 millivolts. Now, if we imagine this resistor R2 as our slide wire, what do we see? By adding an additional resistor in series with our slide wire, we can actually reduce the potential difference across the slide wire to 10 millivolts. Hence, if this slide wire is 1 meter long, then for every 1 meter of the wire, we will have a drop of 10 millivolts, which is, for 1 cm, that is equivalent to 0.1 millivolts. And for 1 millimeter scale, that is equals to 0.01 millivolts. Therefore, we see that even if the cell of a battery is 1 volt, by matching an additional resistor correctly with the resistance of the slide wire, we are able to transform the potentiometer to measure small voltages. This is the typical setup for a potentiometer modified to measure very small EMFs. The typical EMF generated across a thermocouple is in millivolts, but the driver cell is of a typical order of volts. Hence, if we put a resistor, suitable resistor R into the circuit, the sensitivity of the potentiometer can be improved to better determine the EMF across the thermocouple.